Everyone. Before I begin, well, first I would like to thank the organizers for giving me the opportunity to talk here today. It's a pleasure to be here, and well, I hope you will enjoy my presentation. So as announced, I will talk about the BMS group in 3 dimensions. More precisely, the things I will say today are based on the papers that you see appearing here. Most of these were written with my supervisor in Brussels, Glenn Barnish, and the last paper was written in collaboration with Hernan Gonzalez and Alexander Maloney. So to begin, let me first briefly motivate the subject. We all know how special relativity works. It takes place in Minkowski spacetime, whose symmetries are described by the Poincaré group. But of course, the actual spacetime in which we live is certainly not flat. This calls for the question, how can one define a notion of approximately flat spacetimes, or spacetimes that look flat when you look at them from a large distance? This question was addressed in the 60s by Bondi, Metzner, van der Burg, and Sachs, and they came up with a notion of so-called asymptotically flat spacetimes. And they were also able to compute the associated symmetries, which are known as asymptotic symmetries. And surprisingly, they found that the asymptotic symmetry group spans an infinite dimensional extension of the Poincaré group, which is known today as the Bondi-Metzner-Sachs, or BMS group. The BMS group consists of 2 pieces. The first piece is an infinite dimensional group of so-called superrotations, which extend standard Lorentz transformations. And the second piece is an infinite dimensional abelian group of so-called supertranslations, which extend standard space-time translations. Perhaps at this stage I should mention that this terminology of super things has nothing to do with supersymmetry. It simply means that something exists in a finite dimensional context and is extended in an infinite dimensional way in the BMS context. Now, there has been, well, a lot of renewed interest in the past few years in BMS symmetry, and in particular, it is relatively clear that BMS symmetry is relevant both to asymptotically flat holography and to scattering amplitudes in flat space. So in the wake of these considerations, the question that I want to address today is the following. Well, more precisely, it's motivated by this observation, which is that, by definition, what we call a particle is an irreducible unitary representation of the Poincaré group. So the question that I want to ask is, suppose that in this definition, we were to replace the word Poincaré by BMS. Which notion of particle would we then obtain? Now, obviously, this question should in principle be addressed in 4 space-time dimensions. But unfortunately, it turns out that the mathematical structure of BMS symmetry in 4 dimensions is extremely convoluted. Without going into the details, it is such that standard group theoretic techniques simply do not apply to the BMS group in 4 dimensions. This calls for a toy model that would somehow capture the key aspects of BMS symmetry without the complications of 4 dimensions. And therefore, I will talk today about the BMS group in 3 dimensions, or BMS 3.
With the BMS algebra is much larger, so you expect the representations to be much larger, but we know that the particles are already the minimal. Like you can have any particle you want independently.
What do you mean?
Well, so if there were really a larger symmetry at work, I'd expect the representations to be larger, so I'd expect there to be larger multiplets that fit the known particles.
Not necessarily. Not necessarily. This, the size of the multiplets roughly has to do with the rank of the group. And of course, this is not, I mean, neither Poincaré nor BMS are semi-simple groups, so you have to be careful about what you call the rank. But in short, you have to work out what are the parameters that specify an irreducible unitary representation. For Poincaré, it is mass and spin. And then according to your expectation, what you would naively expect is that for BMS, you would have mass and spin and then many other parameters. Remarkably, that is not the case. You actually only have 2 parameters of the type of mass and spin also for BMS.
May I? I have an impression, correct me if I'm wrong, that this BMS symmetry has to do with light-likes, asymptote of space.
Yes, I'll come to that, but yes.
That means that the only particles that can reach it from the bulk are the massless ones, right?
The particles, yes, but the symmetry may also describe massive particles. A massive particle can emit gravitons. So you can see it. And you can measure the massive particle also at non-infinity. You can measure mass at non-infinity. There is a Bondi mass aspect which measures this also for massive particles. And indeed, in particular, at some point we'll come to it and we'll see that there is a very natural analog of massive particles in BMS symmetry. So with this motivation in mind, here is the plan of my, oh, sorry.
I thought that at least some of these were classified by Patrick McCarthy, these representations.
So in BMS4 they were, but you have to be careful about what you call the BMS group. What McCarthy classified were indeed the irreducible unitary representations of what we know today as the global BMS group. That is the BMS group which doesn't quite have this form, but rather has the form of the Lorentz group times an infinite dimensional group of supertranslations. And, well, you might think that this is the end of the story, and it might be. But I think there is well-motivated hope that, in fact, if you add the super rotations, as I will do systematically in this talk, you actually get something way more interesting. And indeed, what McCarthy got was just a classification that looks very much like the classification for Poincaré, which doesn't contain much more, actually.
So you explain to us what are the difference between Lorentz and super rotation?
In 3 dimensions, I will explain it, yes, sure.
Yeah. Is this the difference between 2 plus 1 and 3 plus 1? That is, my memory is in 3 plus 1, well, what used to be called the BMS group was the Lorentz group times the super translations. And the super rotations were ruled out.
Were ruled out by what? Oh, by the fact that they're not global.
For reasons that I don't remember, but I remember the lecture discussing the
So originally, super rotations in 4 dimensions were ruled out because
something didn't fall off the right way.
no, that's not the case. To the contrary, they do fall off the right way, but they define non-invertible conformal transformations of the celestial spheres, in the same way that local conformal transformations in the 2-dimensional CFT are generally not invertible. The only ones that are invertible are those that actually span the Lorentz group. So
then it's not a group?
Sorry?
Then it's not
Exactly. And there is even worse. When you add a central extension, it's really not a group at all. And that's why I said that in 4 dimensions, no one really understands how to do what I'm going to do now in 3 dimensions.
You mean they're like in a Lie algebra and not exponentiatable?
This may be one problem. There is even, honestly, there is even more. In 4 dimensions, as soon as you add a central extension, which naturally appears in gravity, the structure that you get is no longer a group, but what is known as a groupoid. And it's way more complicated to work out. I mean, as far as I know, it's very poorly understood at present.
But is the structure of just the Lorentz group times the super translations understood?
That one is understood. But as I said...
So is there a physical motivation for going beyond that to the super rotations?
Yes.
So you'll explain that.
In particular, the motivation is precise. In part, the motivation comes from what I'm going to say later on, which is that if you actually want to account for soft graviton degrees of freedom, you are bound to add super rotations. If you don't, you really get something which, well, which definitely is interesting, but my impression, well, our impression is that it captures only part of the interesting structure. Good. So with this motivation in mind, the plan of the talk will be the following. First of all, I will review in general terms the theory of unitary representations of semidirect products. Then I will, well, show that the BMS group in 3 dimensions is indeed such a semidirect product, and then I will classify its representations. And finally, I will relate these representations to 3-dimensional gravity. Good. So semidirect products. What I'll do here is first to explain what I call a semidirect product, then to show that unitary representations of such semidirect product groups are naturally associated with the notion of orbits, and in particular, I will display the orbits in the specific example of the Poincaré group in 3 dimensions. And finally, I will write down an explicit formula for unitary representations associated with such orbits. So the Poincaré group, by definition, consists of Lorentz transformations and translations. A bit of notation. The Poincaré group I denote by P. The Lorentz group in 3 dimensions I denote by SO2, 1. And by this, I really mean the connected Lorentz group in 3 dimensions. And the group of 3-dimensional space-time translation is just R3. The elements of this group are pairs consisting of a Lorentz transformation F and a translation alpha. And by definition, the group operation is such that when I compose two Poincare transformations, they contain the resulting composition of Lorentz transformations and the sum of the corresponding translations. The only subtlety is that the Lorentz transformation F acts on the translation beta, and here I denote this action by a dot, which you should really think of as the action of a 3×3 matrix on a 3 vector. This action is the reason for the notation here, and it's the reason why we say that the Poincare group is a semi-direct product. Obviously, this structure can be generalized, so throughout this talk, I will call semi-direct product a group P which is of the form G times A. So here G is generally a non-abelian group. A is an abelian vector group, by which I mean a vector space in which I see the addition of vectors as the group operation. And sigma is some representation of the group G in A. The elements of this group are pairs, F alpha, where F belongs to G and alpha belongs to A. And the group operation is such that, well, the products, there is the element of G on the right-hand side is just the product of the corresponding elements in G. And the abelian element is just the sum up to the action sigma of the non-abelian element F on the abelian element beta. Now, suppose I ask you to give me some unitary representations of such a group. At first sight, the question looks impossible, so we can begin with something much simpler. Namely, we can ask what are the unitary representations of the abelian piece of this group. Since the group is abelian, all such irreducible unitary representations are one-dimensional. They are pure phases which associate with the translation alpha a pure phase e to the IP mu alpha mu. And in the context of Poincare, this triple of numbers p mu is known as the momentum. It will eventually represent the momentum of a particle transforming according to some representation of the Poincare group. And again, these considerations are not actually specific to the Poincare group. I could just as well start with an arbitrary semi-direct product and ask, what are the irreducible unitary representations of the abelian group? Once more, these representations would be one-dimensional. They would associate with the element alpha a pure phase e to the IP alpha, where now this bracket here denotes the pairing between the dual space of A star, and the abelian group A. Now, given some unitary representation of the full semi-direct product, I can restrict this representation to the abelian subgroup of the semi-direct product, and in doing so, I will generally find a reducible unitary representation of A. In other words, I will find a direct sum of many representations of this form specified by many different momenta. So a natural question is, which momenta exactly could we find in such a decomposition? And as I want to argue now, the answer lies in this notion of orbits that I mentioned at the beginning. To introduce orbits, suppose I have a unitary representation T of the semi-direct product in some Hilbert space H. And suppose there exists a subspace V of that Hilbert space on which all translations are represented by pure phases of this form, where P is some specific momentum vector. Now, suppose I pick an element F in the non-abelian group G. Then it's actually very easy to check, using the group operation that I gave on the previous slides, that there certainly exists another subspace V prime of the Hilbert space on which all translations are once more represented by pure phases, but with the key difference now that instead of involving only the pairing of P with alpha, they involve the pairing of P with alpha acted upon by F minus 1. And this would be true for any choice of F. So I can now define an action, which I denote by dot, an action of the group G on the space of momenta by declaring that F dot P is a momentum that satisfies this relation for any translation alpha. And given this definition, what I know on the basis of this argument is that the minimum amount of momenta that I can find in a unitary representation of the semi-direct product here is what I call the orbit of the momentum P, that is the set of all possible F dot P, where F runs over the non-abelian group. Since this is a bit abstract, let me illustrate the notion of orbits for the simple example of the Poincare group in 3 dimensions. In that case, it's actually easy to classify the orbits because, by definition, Lorentz transformations preserve the Minkowski metric. So, in particular, the norm squared, the Minkowski norm squared of any momentum is left invariant by Lorentz transformations. Accordingly, the orbits will be connected hyperboloids specified by an equation of this form in R3. And here, m squared is a parameter that, of course, we call the mass squared. The only exception to this is the trivial orbit of the vanishing momentum. I can draw these orbits here. So for example, the cross here is the vacuum orbit. Then the upper cone is the orbit of massless particles with positive energy. Same thing below, but with negative energy. Then here on top, I have a continuous family of massive particles, well, particles with positive mass squared and positive energy. Same thing below, but with negative energy. And then here I have a continuous family of tachyonic orbits. Now, for future reference, it will be very useful to introduce a schematic representation for these orbits. So let me represent the vacuum orbit by a blob here, the continuous family of massive orbits with positive energy here, same thing here but with negative energy, then the family of tachyonic orbits by this horizontal line, and finally the massless orbit with positive and negative energy by these two blobs. Clearly, at this stage, there's really no particular use for this kind of schematic representation because in Poincaré, we can just draw the orbits and see everything that happens. But you will see that once we turn to BMS, the orbits will be much more abstract objects, and it will be very helpful to keep in mind this kind of schematic representation. So I have now spent some time explaining generic properties of unitary representations of semi-direct products, but I haven't actually written down a formula for such representations, so let me do it now. So suppose we pick an orbit of some momentum p, and let us define a space, a Hilbert space of wave functions on that orbit. Wave functions will be functions psi that associate with the momentum q on the orbit a complex number psi of q. You should really think of these wave functions as wave functions in momentum space. A wave function that is sharply centered around some value of momentum will eventually represent a particle that propagates with that particular value of momentum. Now, I want to define an action, well, a representation T of the group P acting on the space of wave functions. So now I need to tell you what this object is. This object is, of course, a wave function. So in order to define it, I need to tell you the value that it takes at some particular momentum q. Now, recall that the very reason why we introduced orbits in the first place was to represent translations by pure phases. So it's natural that on the right-hand side here, the first term is just an exponential of the translation alpha paired with the momentum q. The only remaining ingredient that we need to find is the argument of the wave function here on the right-hand side. And as you can easily check, the only choice that gives rise to representation is to act with f-1 on the momentum q. In fact, the formula that I just wrote defines an irreducible representation of the semi-direct product P. Of course, what I want to do is slightly more, because I don't only want irreducible representations, I want them to be unitary. And, well, there's a very easy way to turn this representation into a unitary one. Namely, if I have a measure mu on the orbit, and here for definiteness, I'm assuming, well, actually for simplicity, I'm assuming that the measure is invariant under the action of g, but this assumption can be relaxed. Given such a measure, I can define a scalar product of wave functions by declaring that, well, the scalar product of these two wave functions is the integral of their product over the orbit with a complex conjugation on the first argument. With this scalar product, the representation that I wrote is irreducible and unitary. And in fact, the reason why I'm spending time to describe these representations is that there is a result or theorem in mathematics due to Mackey, which states that all irreducible unitary representations of a semi-direct product are representations of this form. Strictly speaking, this theorem is slightly, well, the theorem holds, but the representations that satisfy this theorem are slightly more general than the ones that I showed here, in that the representation that I wrote down here is actually a scalar representation, a representation with vanishing spin. You can just as well generalize the whole construction to spinning representations, but here for simplicity, I'm going to focus only on scalar representations, which indeed will be sufficient to see most of the interesting features of BMS representations. Question? Yes, go on.
This might not apply to scalar representations, but in general, don't you want projective representations as opposed to ordinary representations?
Sure, yes.
Like get half integer spin and so on.
I mean, so in fact, in 3 space-time dimensions, you can have literally any real value of spin you can imagine, precisely because you can in principle have projective unitary representations. So here in this talk, whenever I say unitary representation, the word projective is understood. It's there. I just don't mention it. But sure, I mean, having projective representations is completely OK. In fact, it will be essential once we turn on the central charge, because the central charge is a way to make projective representations. Good. So this is all I had to say in general about unitary representations of semi-direct products. So now I can turn to BMS. Here I'll do two things. The first is to write down an explicit definition for the BMS3 group. And the second is to show you how one can classify the corresponding orbits and therefore the corresponding unitary representations. Now, the BMS3 group is in principle defined as the asymptotic symmetry group of three-dimensional asymptotically flat spacetimes. To be a bit more precise about what I mean by this, here is a Penrose diagram of Minkowski space where I display the three coordinates that I will use. So that's my computer. OK. So there's a radial coordinate, r, such that the region where r goes to infinity is future null infinity. Future null infinity itself is a cylinder spanned by a null-time coordinate u and an angular coordinate phi, which, well, on the celestial sphere, which ranges from 0 to 2 pi. Well, actually here on the celestial circle. In terms of these coordinates, saying that the metric is asymptotically flat is saying that as r goes to infinity, the metric takes the Minkowski form up to certain subleading corrections. And there is a precise definition of what we mean by subleading in this context, but again, for simplicity, I'm not displaying this explicit definition here. Given this definition, one can start looking for diffeomorphisms of space-time that preserve these fall-off conditions on the metric. And in principle, this is, well, a computation, a relatively long computation, which I'm not going to display here. So instead, I'm just going to flash you the result. It turns out that if you work out the asymptotic symmetries of asymptotically flat metrics in this sense, you find asymptotic symmetries that fall in two classes. The first class are arbitrary diffeomorphisms of the celestial circle, and the second class are arbitrary angle-dependent translations of the null-time coordinate u. In the BMS context, these two families of transformations bear special names. Namely, the first family are known as super-rotations, and the second family are known as super-translations. I will return to the origin of this terminology shortly, but before doing this, let me just mention one important point, which is that if you perform simultaneously a superrotation and a supertranslation, the transformation of time involves, in addition to the function alpha, the first derivative of the diffeomorphism f here. And this derivative is actually crucial in order to define the group operation in BMS3. The reason for the terminology of superrotations and supertranslations stems from the fact that these transformations span an infinite-dimensional extension of the three-dimensional Poincare group. For example, space-time translations in 3 dimensions are represented by supertranslations alpha, in which only the 3 lowest Fourier modes of alpha are switched on. In particular, time translations are represented by functions alpha that are constant on the circle. Similarly, rotations of space are represented by superrotations which simply take the form f mapping phi on phi plus theta. And in a similar way, there is a way to represent Lorentz transformations in terms of certain specific superrotations, but since I will not need this formula here, I'm not going to display it explicitly. And again, I should mention that this has nothing to do with supersymmetry. Great. So now we know that BMS transformations are actually pairs consisting of a superrotation f and a supertranslation alpha. Yes?
I had a question when you go back. When you say r goes to infinity,
yes.
Does that include sort of r going to scribe plus, r going to scribe minus, and going to space-like infinity, or is it only going to scribe plus?
No, scribe plus. Here I'm taking scribe plus for definiteness.
There's a physical question which I never really understood the answer to. Is that why do you only limit yourself to scribe plus? I mean, there's 3 parts of the boundary.
Sure.
If we were to go space-like, we might just go back to the Poincare group, or do you have some words of wisdom about why scribe plus only?
I don't think I do, but well, OK, one thing is that it seems to be crucial to go at null infinity. So then you have 2 choices, scribe plus or scribe minus. Doing one or the other is essentially the same up to certain changes of changes of notations and conventions. So on the other hand, there are also claims that unpublished claims, but that I've heard by people working in the field, who say that in fact you can define BMS3 also at spatial infinity. But as I said, this is unpublished, and I'm not sure if it will be published ever because it seems to be controversial. So somehow it appears crucial to go at null infinity. Why physically this is so, I mean, in 4 dimensions, I could have the interpretation that this is so because that is the region where you can actually see gravitational waves going in and going out. But in 3 space-time dimensions, there are no gravitons to begin with. So I don't really know, to be honest. It just so happens that this is the easiest way to introduce BMS. Interestingly enough, in the end, you see, I mean, I introduced BMS here by going to future non-infinity, square plus. But if you look at these group elements here, F and alpha, they never involved time. They only involved the coordinate phi on the circle. And in fact, the same would be kind of true in 4-dimensional BMS, where these transformations would actually only depend on the coordinate z, z bar on the celestial sphere. So somehow, this null-time coordinate is necessary at the beginning to define the group. But once you have defined your group, you can actually completely forget about it and work just here on a circle and in BMS4 on a sphere.
Well, but your second thing does change the time.
It does change the time. It does change
it. That's the physical meaning of it, even though you might say mathematically.
Yes, but then, I mean, so there will be a formula that will appear here for the BMS group, which will not involve time in any way. It will be something defined entirely in terms of functions on the circle. That is what I mean by the fact that, of course, a super translation is a translation of time. So you always have in the back of your head that that's what it means. But you can define it regardless of this. Yes?
Yeah, is behind this are the particular fall conditions you choose.
Yes.
Is there some dynamical principle having to do with preserving a symplectic structure or preserving the form of action or preserving some that tells you what those should be?
So as far as I know, one of the fathers of boundary conditions in 3-dimensional gravity is Marquenot. And in his own words, finding boundary conditions in 3-dimensional gravity is an art, not a science. So, of course, you might wonder why we are defining such boundary conditions. All I could say is essentially the same motivation that led Brown and Eno to their boundary conditions back in the 80s, which is that you want to devise boundary conditions that include sufficiently interesting solutions, such as obviously you want to include, in this case, Minkowski space, but you also want to include conical deficits, conical excesses, and then you want this to be you want your asymptotic symmetry group to at least contain Poincaré. If you do this, the minimal boundary conditions that you find are essentially those that I wrote. In the same way that in ADS, if you include the existence of ADS space, conical deficits, and the existence of an SO22 asymptotic symmetry, you find Virasoro plus Virasoro, and you find the Brown-Eno central charge.
So that is one way to talk about it, but for example, Kurosh and Ashtekar developed another way to talk about it in terms of differentiating gauge transformations from global symmetries in terms of preserving certain charges or algebras and charges that.
Isn't that equivalent to
well, if your art is working well, it is equivalent. If it's a different starting point. If the science of the art of finding boundary conditions works out for you and you're lucky, it is the same.
Yes.
But it's a subtle thing to work out in 3+1.
Oh, you mean in 3+1? Because generally in 3+1 charges are non-integrable, you mean, or something like that?
Well, the question of how many charges are there which are non-vanishing on physical solutions. So how many multiple moments of charges are of interest in what algebra they have under the symplectic structure. It's all part of goes into what the choice of boundary fallout conditions are.
Yes. Yes, this I definitely agree, yes. So what puzzles you about these boundary conditions here specifically?
Are you going to discuss in 2+1 the analogous issues of separating global charges from diffeomorphisms and so forth? Right. So you mean, is there a dynamical argument why I would choose certain boundary conditions that would effectively help me distinguish what a diffeomorphism is and what a global transformation is? Exactly.
Okay, I don't have any better answer than what I essentially gave, which is that, well, what could have happened is that you define these boundary conditions that, as I said, include in ADS. They would include SO22 and conical deficits in ADS. And then you might find that, in fact, they all have vanishing charges. They're all gauge symmetries for some reason. That could happen. Why it doesn't happen, I don't know. It appears, I mean, you could, in the case of ADS3, you could say that it's because of ADS3 CFT2, that you need to have a CFT2 at the boundary. But then, I mean, that's answering the question by itself, by saying that, you know, the answer has to, I mean, why is the answer non-trivial? And then you would say, well, because the answer is non-trivial. Well, OK, but it doesn't work. So I don't know, honestly. I mean, what I'm sure about is that these boundary conditions, I mean, the boundary conditions that I'm explaining here, or equivalent to the Brown and O ones, are natural in the sense that actually there are results in three-dimensional gravity that explain that, for example, in ADS, you can essentially define only three different classes of boundary conditions. The first ones are trivial in the sense that they include only two charges, energy and angular momentum. The second ones are the Brown and O ones, and the third ones are relaxed Brown and O. Brown and O with an arbitrary, well, with a fluctuating conformal factor in front of the metric at the boundary. And you cannot relax them more than this, and you cannot relax them less than the first thing that I said. So you have essentially just three choices. Now, why nature? Well, nature, of course, is four-dimensional, so nature doesn't really care much about 3 dimensions, I think. But why one of those three choices would be the canonical one, I don't really know. Good. So BMS transformations are pairs consisting of a superrotation F and a supertranslation alpha. And now, in order to define the BMS group, we need to know the group operation. Well, in order to answer this, we simply need to compose two such transformations.
Sorry to interrupt again, but I guess you're not going to come back to 4 dimensions, so.
I am not. Perhaps in the very end of the conclusion when I say what I want to do in the future.
Okay. Are these super rotations the same thing in 4 dimensions? Are they arbitrary diffeos of?
No, no. So the first thing to note is that here superrotations are globally well defined. Yeah. And in fact, this is the reason why we can do all this in BMS3. Yeah. In 4 dimensions, superrotations are, well, there is a certain amount of debate in the literature about this, but I think that for the moment, the safest is to say that superrotations in 4 dimensions are arbitrary local conformal, generally non-invertible conformal transformations of the celestial spheres. So they are not arbitrary diffeomorphisms of the celestial sphere, but conformal transformations. Then I know of at least one paper, perhaps there were follow-ups, that claims that there exists a suitable generalization of superrotations that would include arbitrary diffeomorphisms of the sphere. But, well, OK. I have no claims about this. I don't know. I don't dare saying anything. Good. So, indeed, so the group operation, in order to find the group operation, what we need to do is compose two such transformations. And if you do this, what you find is that the superrotations simply get composed together, and the supertranslations add up to an action that I denote by sigma of superrotations on supertranslations. And this action is explicitly given by this formula here. The nice thing about this formula is that in it, you can recognize the transformation law of vector fields on the circle under diffeomorphisms of the circle. In other words, these superrotations, which so far I thought of as functions on the circle, well, from now on, I will rather think of as vector fields on the circle, functions of quantities of this type. And with this very slight change of viewpoint, there is actually a very natural definition for what we call the BMS group in 3 dimensions. Namely, it is the semi-direct product of the group of diffeomorphisms of the circle with the abelian vector group of vector fields on the circle. And the action of the left factor on the right one is just the natural action of diffeomorphisms on vector fields. So this definition obviously shows that BMS is a semi-direct product in the sense that I explained. So we can now start looking for its representations. But before plunging into the computations, I think it's worthwhile asking what we should expect from these representations on physical grounds. So to answer this, let me use Poincaré as a guide. The Poincaré group is the isometry group of Minkowski spacetime. It is an exact spacetime symmetry. And as I said in the introduction, its irreducible unitary representations represent the degrees of freedom of a particle propagating in Minkowski space. Now, the BMS group, on the other hand, is an asymptotic symmetry group. In other words, it is the generalization of the Poincare group that is suitable when including gravitational fluctuations. So physically, what we should expect from a unitary representation of BMS is that it essentially represents a particle dressed with certain gravitational degrees of freedom. And in accordance with the relation between BMS symmetry and soft gravitons, in fact, these degrees of freedom should be soft gravitons. From now on, I will call such representations of BMS, i.e. particles dressed with soft gravitons, I will call them BMS particles. In quantum mechanical terms, what this means is that we expect the Hilbert space of a BMS particle to be the tensor product between the space of states of a standard particle, which I denote by this symbol here, and a certain more abstract space of soft graviton degrees of freedom, which at this stage is very mysterious and, well, I didn't even define it, so it may not exist.
What do you mean by soft graviton in 3D?
Exactly. So that's of course a valid question. In 3 dimensions, there are no gravitons to begin with.
So it's addressing by something else.
So, sorry?
It's addressing by something else. You still have a long-range gravitational field.
Exactly. You have. People generally call these actually boundary gravitons, but the.
That's not what I mean.
Sorry.
That's not really what I mean.
They
have spin 0.
Why do you say they have spin 0?
Well, because there's a scalar mode. There's always the Newtonian mode. I guess you're addressing it by the Newtonian mode at best. But there are no gravitons anyway.
There are obviously no gravitons, that's for sure. But there are non-trivial degrees of freedom which are topological. I wouldn't say that they have spin 0, because when you compute the one-loop partition function, you can actually see spin 2 degrees of freedom that are cancelled by spin 1 ghosts.
Yes.
And indeed, there are as many ghosts as spin 2 degrees of freedom, but they still have spin 2. So in this sense, I would definitely call them.
What about the spin 0?
In the one-loop partition function, it does not appear. Or more precisely, it is, well, there's a spin 0 mode that is cancelled by one spin 0 ghost. And so that one you really don't see even in the rotating partition function. But what you do see is that the spin 2 degrees of freedom are not exactly cancelled by the spin 1 degrees of freedom because they have spin, they rotate in different ways. But indeed, so if you are unhappy with me using the word soft graviton in 3 space-time dimensions because there are no gravitons to begin with, then you can just think of these soft gravitons as the topological degrees of freedom of asymptotically flat gravity in 3 dimensions. But I dare calling them soft gravitons because in 4 dimensions, that's exactly what they would be. In 4 dimensions, the boundary gravitons are soft gravitons. Boundary gravitons, which also I'm not using the terminology of boundary gravitons because I had a debate, a 1 hour and a half long debate with Glenn when I said I wanted to put them in, and he said he didn't, and he ended up convincing me. So I agree that boundary gravitons is a dangerous terminology. But soft gravitons, well, it's dangerous if it's misleading, but I don't think it's misleading if I explain what I mean, in this case at least. So as I said, so far the space of soft graviton or boundary graviton or topological degrees of freedom of gravitons that I explained here is very abstract. But assuming that we could actually do something like this, there are several natural questions that follow. The first is, well, you know, in Poincare, we can actually classify particles according to mass and spin. So can we do something similar for BMS? And if we can do this classification, can we actually describe this space here of soft graviton degrees of freedom? And third, assuming that we can even do the first 2 steps here, can we actually make some use of it? Can we compute something physical using these ingredients? And in the remainder of the talk, I want to argue that the answer to all 3 questions is yes. So let me now describe the orbits that are used to classify unitary representations of BMS. BMS, as I said, is a semi-direct product of this form. And you may recall that the first quantity we needed in talking about these representations was what I call the space of momenta, the dual space of the abelian group. In the case of BMS, abelian elements are known as supertranslations. So it is natural for me to call elements of the dual space supermomenta. In practice, a supermomentum is just a function p on the circle, which is paired with supertranslations in a linear and real-valued way. In practice, this pairing is just the integral of the function p multiplying the function alpha over the circle. Now, given the interpretation of supertranslations, there is a natural interpretation for the lowest Fourier modes of P. Indeed, time translations are represented by functions alpha that are constant on the circle. So the zero mode of the supermomentum P should be interpreted as the energy associated with P. And similarly, the modes P1 and P minus 1 should be interpreted as certain complex linear combinations of the components of spatial momentum. Now, in order to classify representations of BMS, we need to classify orbits of supermomenta. In other words, we need to fix a certain supermomentum P and to find all the possible F dot P where F runs over all possible superrotations. Now, F dot P, by definition, was defined, well, F dot P was defined in such a way that when I pair it with alpha, this relation holds. And now, if you look back at the formula that I gave for this pairing and at the definition of the action sigma in the case of BMS, you will actually see that F dot P, seen as a supermomentum that I evaluate at the point f of phi, is simply P divided by the square of the derivative of F. If you keep in mind two-dimensional conformal field theory, you can recognize in this formula the transformation law of a primary field with weight 2 on the circle, if you think of superrotations as conformal transformations in one dimension. But at this stage, I have to say that I cheated a little bit in that the group that I defined, strictly speaking, well, did not include central extensions. But of course, central extensions tend to appear and do appear either in quantum mechanical applications or already classically at the level of surface charges in gravity. So the group that I should have defined, really, was the central extension of the group that I wrote down here. And had I defined such a central extension, I would have found that the duals of supertranslations include indeed a supermomentum P of the form that I described here, but also include a number, a parameter, which I will denote by C, and which is actually a central charge. This central charge is just, as I said, a number, a parameter, but crucially, it appears in the transformation law of the supermomentum, and it appears in this form. So C here is the central charge, and what I denote by a curly bracket between F and phi is the Schwarzian derivative of F. If you don't remember what the Schwarzian derivative is, never mind, just keep in mind that it's a complicated combination of derivatives of F. So what this formula tells us is that in the centrally extended BMS group, which is indeed the one of physical interest, the transformation law of the supermomentum P is actually that of a quasi-primary field with weight 2 on the circle. That is the transformation law of the stress tensor of a CFT stress tensor on the circle, if we think of superrotations as conformal transformations in one dimension. And the nice thing about this is that, well, now it tells us which orbits we are supposed to classify. What we really need to do is to classify orbits of CST stress tensors under conformal transformations. And remarkably, these orbits have been studied by many people, first by mathematicians, then by physicists ever since the 70s, and they are known as coadjoint orbits of the Virasoro group. So what I'm going to do now is to briefly describe the classification of these coadjoint orbits. In principle, what we need to do is to fix a supermomentum and find all the possible F dot P. This defines the orbit. Since there are infinitely many linearly independent diffeomorphisms, well, I don't want to talk about linear independence. The group of diffeomorphisms is an infinite dimensional manifold. That would be more precise. So this orbit here is necessarily an infinite dimensional manifold. So obviously, it's a very complicated question. So to make it a bit simple, well, let me introduce the two following simplifications. The first is that instead of considering an arbitrary supermomentum P with, in general, a non-trivial profile on the circle, I'm going to consider a constant one that takes some value P0 on all points of the circle. In physical terms, you should really think of this as considering a frame where the particle we're describing is at rest. The only non-zero component of its energy momentum is energy. With this simplification, the function P here really becomes just a constant P0. The second simplification is that instead of looking for the full orbit, I am rather going to look for the stabilizer of the supermomentum P. In other words, I'm going to look for superrotations F that satisfy this equation here, which in principle is a very complicated differential equation for F. If I find the stabilizer, in fact, I essentially know the orbit because the orbit is a homogeneous space, so it is diffeomorphic to the quotient of the group of superrotations by the stabilizer. And so, again, here, is a several-page computation that I'm not going to display, but instead I'm simply going to give you the result. The result is the following. For generic values of the constant P0, you find that the only elements of the stabilizer are rigid rotations of the circle, and they span a group which is just a group U1 of rigid rotations. But there turn out to exist exceptional values of P0, which are of this form, with C, the central charge, and N, a strictly positive integer. And it turns out that for such values of P0, the stabilizer indeed includes, again, all rigid rotations, but it also includes some additional terms, which I'm not writing down for simplicity, which effectively enhance the stabilizer from a group U1 to an n-fold cover of the Lorentz group, which is three-dimensional. So let me summarize these findings in a diagram of the orbits. So here, the vertical axis is the axis of P0, and for definiteness, I'm putting the origin here. What I just said is that for generic values of P0, the stabilizer is U1, and the orbit is therefore diffeomorphic to this quotient space. I also mentioned that there exist exceptional values of P0, which are labeled by this positive integer n. So here is, for example, n equals 1, here is n equals 2, here is n equals 3, and so on. For such values...
So where is your signature here? P0 negative means what?
Excuse me?
P0 is negative. What does that mean?
Negative, what do you mean? Oh, negative here.
Minus n squared. So
why is that a problem?
well, it's supposed to be an energy momentum tensor. So
Yes, but I didn't tell you
that corresponds to negative energy, or what?
Yes, indeed. No, a CFT on the cylinder generally has negative energy because the vacuum energy is at minus C over 24.
So an example of such a solution is what?
The vacuum.
Singularity?
The vacuum. So, okay,
So
this
the
is...
vacuum has only one.
The vacuum is here. So the vacuum is at P0 equals minus C over 24, which is the natural vacuum value of
The other ones are like particle naked singularities?
Sorry, these ones. These ones on the gravity side are conical excesses. Actually, so these are conical excesses by an angle of 2 pi n minus 1. Or, well, more precisely, those are such that when you wind around the origin once, you have to make an angle of 2 pi n. In particular, this one is not a conical axis. It's just the vacuum. It's just Minkowski space from the gravity.
So 2 pi over n or 2 pi n?
2 pi n. 2 pi n.
Which means it's kind of opposite to the particle, right?
Exactly.
The particle is a conical
Indeed.
and this is
Exactly. The particles will actually be here.
Yeah, and the black hole will be
Except there are no black holes.
yeah, if you were in
Exactly. In ADS, those would be black holes, those would be conical deficits, and those would be conical excesses. And again, in flat space, those are indeed conical excesses, those are conical deficits, and those are so-called cosmological solutions, which I'm not really going to talk about much. Great. So this is already a nice result, but obviously this was an oversimplification of the problem, so we must be missing something. So what are we missing? A very simple way to find the remaining orbits is to consider perturbations of constant orbits. And in particular, it turns out that if you perturb an exceptional constant of this form by some small perturbation delta p, and if you consider this as a new supermomentum, you may ask, well, what is going to be the orbit of this supermomentum here? And it turns out that this perturbation delta p here transforms under the stabilizer of this exceptional constant as a 3-momentum vector. In other words, you should really think of this as a kind of Poincare momentum specifying a small perturbation around here, and for each value of n, around any such constant value, we find a copy of Poincare orbits. And in fact, these are precisely the new orbits we're looking for. So for example, around n equals 1, we already have this vacuum orbit. We have the 2 orbits with positive mass squared in this sense. And now we also have a continuous family of tachyonic orbits. We have one massless orbit with positive energy and one massless orbit with negative energy. The same thing now is true for n equals 2, albeit with different Fourier modes, where we again find a continuous family of tachyonic orbits and 2 massless orbits. And again, the same is true at n equals 3, at n equals 4, and at any higher value of n. Remarkably, while this argument is, well, as you can see, tremendously simple, this is in fact the full classification of orbits of supermomenta for specifying representations of BMS. Each orbit determines certain unitary representations of BMS, that is, certain BMS particles. And the Hilbert space of such a BMS particle consists of wave functions on the orbit. Now, there are two families of orbits that I want to describe in a bit more detail because they will be physically important. The first is the vacuum orbit, which is the orbit that contains the constant supermomentum, which is of this form, which is really the point n equals 1 here, where you can recognize the vacuum value of a CFT stress tensor on a cylinder. And the second family of BMS representations that I want to describe, well, that I want to mention, rather, are massive BMS particles, which are all those particles that contain, whose supermomentum orbit contains a constant which is above the vacuum value. So those are really the particles here. As we mentioned briefly, from the viewpoint of representation theory, I would tend to call all these guys massive particles. But from the side of gravity, you can actually, well, I'll mention this later, but these are not quite particles, but so-called cosmological solutions, which I'm not really going to talk about for simplicity. So now, in principle, we have the full classification of unitary irreducible representations of BMS, and we can try to relate these representations to gravity. So I want to do two things. The first will be to relate the supermomentum to what is known as the BONDI mass aspect, and the second will be to establish a relation between characters of BMS and gravitational partition functions. So given the asymptotically flat fall of conditions that I mentioned in section 2, one can ask, what is the general solution of Einstein's equations in 3 dimensions that satisfies these fall of conditions? And again, there exists an explicit formula, which I'm not going to display in full gory detail here. I'm just going to focus on the terms that interest me. Namely, the metric turns out to take this form up to certain terms that, as I said, I'm going to throw away. The important thing in this formula is that, well, the general on-shell metric involves one function that I call P of phi, which is completely arbitrary. And this function turns out to have a physical interpretation because it is actually the BONDI mass aspect associated with this metric. In other words, it is the energy density carried by the gravitational field at null infinity. Now, since this metric is asymptotically flat, yes?
Do you have sources here, or are you just talking about the asymptotic behavior of the metric? Could be a solution, or you mean a global solution?
So what you think, when you say sources, you mean that I'm actually solving Einstein's equations with some non-zero stress tensor. So indeed, typically what you're going to get is that, so okay, again, spoiler. When P is minus C over 24, where C will be some function of the Newton's constant material, which I mentioned, you just obtain Minkowski space, so there is no source. But when P is above minus C over 24 and below 0, what you're really solving is Einstein's equations with the delta function source in the middle of space-time. So these are really vacuum Einstein's equations everywhere but at the origin. The only exception to this is when P is positive, you actually indeed solve vacuum Einstein's equations, but you get something that is like known as a cosmological solution. So since these metrics are asymptotically flat, there certainly exists a well-defined action of BMS transformations on them. And in particular, BMS transformations must act in a well-defined way on the BONDI mass aspect. And if you work out the transformation law, what you find is that the transformation of P is precisely that of the supermomentum, which explains why I called it P to begin with a specific value for the central charge C, which is 3 over Newton's constant. So the central charge in this case is essentially the Planck mass. So remarkably, what we find is that this very abstract quantity that we introduced on purely group theoretic grounds and that we call the supermomentum actually appears in 3-dimensional gravity and has a straightforward interpretation as the BONDI mass aspect. I would like to stress just how natural this is, because the supermomentum is really something like an infinite dimensional generalization of energy momentum that is something like an energy density on the circle, and the BONDI mass aspect is precisely an energy density on the circle, so it all works out pretty well. Using this identification, now you can start analyzing, well, matching representations of BMS to metrics, that is, to actual gravitational fields. In particular, for the vacuum value of the supermomentum, which, as I mentioned, is minus C over 24, if you plug this value here, the metric that you find is actually the metric of Minkowski space, which is very natural because you would expect Minkowski space to be indeed the vacuum metric in the system. So if I had more time, I would now spend some time explaining that this relationship is really just the tip of an iceberg, which is a much deeper relation between on-shell asymptotically flat metrics and BMS representations. The punchline being that it turns out that the quantization of the BMS orbit of a metric actually coincides with the BMS particle. So a BMS particle can be interpreted as the quantization of gravitational fluctuations around the metric. And here when I say quantization, I really mean geometric quantization in the sense of mathematicians. But instead of talking about this, let me talk about the relation between characters and partition functions. So to anticipate the relation is actually very easy because, as I said, the BMS particle is really a particle dressed with soft gravitons. Now, according to my definition of what I call soft gravitons here, in 3 dimensions, all gravitons are soft. So if here I simply take the vacuum, no particle at all, the vacuum BMS particle really just consists of all possible gravitons in 3 dimensions. Accordingly, the character of the vacuum BMS representation should coincide with the partition function of gravitons on Minkowski space. To check if this proposal holds, I now need a formula to compute characters. In particular, I should mention that until the end of this talk, I'm only going to focus on the left side of this correspondence. The computation of the gravitational partition function, I'm not really going to explain. So what we need is a way to compute characters of representations of semi-direct products. Recall that in that context, the key ingredient was the orbit. And by definition, the character of a representation is the trace of the operators that represent group elements in this representation. Now, for the representation that I described, the character turns out to take roughly this form. I should already mention that there is one term missing here, which I'm going to introduce. But this already is very natural because mu is the measure that I used to define the scalar product of wave functions. And these exponentials are just the exponentials representing translations that I introduced from the very beginning using orbits. As I said, there's a missing ingredient here because, as you can see, this does not involve the group element f in any way. And it turns out that the group element f kicks in the delta function here. Now, I should mention that this delta function is crucial for the formula because if you naively look at the formula, what the formula instructs you to do is to integrate something, which naively looks very complicated, over an orbit. Now, for the Poincaré case, the orbit is a finite dimensional manifold, so you're fine. But in BMS, the orbits are infinite dimensional manifolds. So in principle, you are supposed to compute a functional integral. But the delta function actually tells you that you must integrate only over those points of the orbit that are left invariant by f. And if you're lucky, there's actually only one such point, and then you're basically done. You can just do the computation. So let's see how this works for the case of a massive BMS particle. So by this, I mean that I'll take a BMS particle specified by the orbit of some constant supermomentum P0, whose orbit is this infinite dimensional manifold here. Also, I will take for definiteness f to be a rigid rotation by some angle theta. So the character that I want to compute is this horrible integral here. Now, a rotation by theta acts on a supermomentum q by mapping it on a new supermomentum, which is simply the old supermomentum rotated by an angle theta. And now from this, it's very easy to see that, at least for generic values of theta, the only supermomentum that is left invariant by this rotation, that is, the only supermomentum which will actually contribute to the integral because of this delta function here, is the supermomentum of the particle at rest. It is the only one that contributes to the integral is the constant supermomentum. So we're precisely in the case that I was advertising earlier, which is where this integral, naively horrible, actually simply boils down to an integral over one point. With this simplification, for example, the phase here can be replaced simply by the product of P0 with alpha 0. And the only thing that remains to be done is to integrate the delta function. For this, I introduce coordinates on the orbit. And in this case, because I'm describing a massive particle, these coordinates will really be the non-zero Fourier modes of supermomenta. These Fourier modes transform like so under rotation by theta. So this integral here, or the delta function, is really a product of infinitely many integrals over momenta. Integrals over Fourier modes. And this, in turn, gives me this kind of factor here. And in principle, at this stage, I'm done. This is the full formula for the character of a rotation by theta, supplemented by an arbitrary supertranslation, in a massive representation of BMS. As you can see, however, this infinite product here is actually divergent. So what you need is, well, in order to make sense of it, you're supposed to regularize it in some way. And a natural regularization, which can be seen as a remnant of the result that you would obtain in ADS, consists in adding a small imaginary part to the angle theta, as displayed here. Now, this character is the one for a massive BMS particle with supermomentum at rest P0. You could do the same computation for the vacuum representation. We call that the vacuum has P0, which is minus C over 24, so you can see it here in this exponential. And exactly in the same way as for massive particles, you would obtain a kind of infinite product like this, but with the key difference that the product in the denominator here starts at n equals 2 rather than n equals 1. And this truncated product comes from the fact that the vacuum is Lorentz invariant, which is not the case of a massive particle. So this is the vacuum character of BMS. You can write the same character for a Euclidean time translation by beta, say, and you would obtain exactly the same result, but then the exponent here would be replaced by this combination. And in our work with Glenn Barnish, Hernan Gonzalez, and Alexander Maloney, we showed that, in fact, this expression here coincides with the one-loop partition function of gravitons on thermal flat space at temperature 1 over beta and with an angular potential theta. And, well, this result is actually the Minkowskian analog of a result that was known already some time ago in the context of ADS CFT. So this brings me to the end of my talk, so I'm just going to briefly summarize what I said. What I explained is that the BMS group is a semi-direct product consisting of superrotations and supertranslations. So the key quantity that classifies its representations are supermomenta, or more precisely, orbits of supermomenta, which, as I said, are actually coadjoint orbits of the Virasoro group. And this classification, in turn, can be used to relate BMS particles to gravity. In particular, the supermomentum is really just the BONDI mass aspect. A BMS particle is a particle dressed with soft gravitons, or equivalently, the geometric quantization of the orbit of a metric. And finally, BMS characters coincide with one-loop partition functions of gravitons around flat space. And I guess I will stop here. So thank you for your attention.
Questions? Raise your hand. Oh, yeah. There's something very simple that I didn't understand about your last point, the relation of the character to the partition function.
Go on.
I don't think you told us much about the partition function directly, but there's a simple, there's something I'm not getting. The character is a function on the group. In what way is the partition function a function on the group? Function on a group related to partition function.
So indeed, the character.
Class of
I see.
Space-time are we integrating over to get?
So indeed, the character is a function on the group, but recall that the character is a function. Actually, it's a function on conjugacy classes of the group. Yes. So in particular, the reason why I chose F to be a pure rotation is that essentially any diffeomorphism of the circle is conjugate to a rotation. So roughly any BMS element, any BMS character can actually be written in this form, almost any. And on the side of gravity, the relation between the character and the partition function comes about from the fact that this rotation by theta is really, I mean, BMS is an asymptotic symmetry group, so it is specified by certain transformations of space-time, and you can compute the partition function that you obtain when you take thermal Minkowski, when you take Minkowski space, on which we define certain fields. In this case, the gravitational field in 3 dimensions described by the Einstein-Hilbert action and the associated ghosts, and you can perform, you see, you can evolve your fields in Euclidean time and then declare that after a certain Euclidean time beta, you perform a group operation, a transformation, which in this case is a rotation by theta, and then you glue it back together. And that's where the relation between the character and the partition function comes about.
Are you aware of this work by Alok Labra and Miguel Camperia where they're talking about generalizing the 4D BMS group to diff S2 times, I mean, symmetric product with the super?
Yes. We talked about it yesterday, I think, also. And I mentioned it actually now briefly at some point. I mentioned that diff S2 could appear, yes.
Right, so...
I mean, I have to say I'm remotely aware of it. I'm aware that it exists, but I cannot, yes. So go on.
No, I was just wondering if you thought about that to generalize this to one higher dimension.
I mean, so let me put it this way. Computing the one-loop partition function of gravitons on rotating Minkowski space in 4 dimensions is easy. This you can do, essentially by the same techniques as the ones we used in 3D. In fact, I think I'm even able to compute the associate character in BMS4. Even though I don't know what BMS4 is, as I said, I don't really know the definition. But I mean, certain things must work. You know that the vacuum is going to be Lorentz invariant, so you know which modes you have to mod out when you perform when you compute the character. So it's easy to have a conjecture for the character. And if you compare this conjecture to the one-loop partition function, you see that they don't match at all. Whether the generalization to DFS2 would work, honestly, I'm not quite sure, because there's a very good physical reason why you would want to have not DFS2, but rather the group of, well, the semi-group of local conformal transformations of the sphere, because it is a group of conformal transformations, which includes as its global subgroup the Lorentz group. Now, I'm not sure that what you would call the global subgroup of DFS2 would also be the Lorentz group. It could be something else. Maybe it is, by the way, but I mean, using conformal transformations of the sphere rather than arbitrary diffeomorphisms of the sphere is kind of natural.
So there's something else I'm confused on, which it seems the mass represents, I mean, geometrically in the gravitational side is something like a defect angle
Yes.
of a cone. So I would have thought that that was somehow super selective, because different defect angles correspond to different asymptotic metrics. And you've asked for the you've asked for the group, sort of generalized BMS group, which is supposed to be that which preserves the asymptotic form of the metric. So to change the mass seems to me does not preserve the asymptotic form of the metric.
I never said that there exists an asymptotic symmetry transformation that maps a particle with mass m on a particle with mass m prime. And in fact, the whole point of this classification is that there is no such transformation.
Okay.
So
then is the mass is that supposed to be a super selective quantity then?
A super selected quantity.
In other words, you have a different set of representations for each value of this mass.
Yes, sure.
They're completely physically disjoint.
They are, I mean, different masses correspond to different representations in the same sense as in Poincaré. In Poincaré, if you have a particle with mass 2 kilograms, sorry?
Go ahead.
You cannot use a Poincaré transformation to change the mass of a particle. That's the mass is an invariant. In the same way here, you cannot change the value of P0 at rest, if that is your question.
This is true, but if you have two particles, for example,
okay,
you can have superpositions of different, in the same Hilbert space.
Yes.
You have superpositions.
Yes.
Mass.
So then your Hilbert space would be the tensor product of of the Hilbert spaces of BMS, two BMS particles.
I'm not sure that makes physical sense. At least I'm not sure it's compatible with the starting assumptions that led you to this BMS group.
Okay, this I don't know. This I don't know. It's actually, I mean, I already thought of what would happen if we were to use this representation theory to represent the evolution of two particles into two new particles or something like that. But I don't know how that would work. So I prefer not to make any claims.
Okay, and related questions. Classically, again, we're talking about really, I think, a small number. When you're talking about solutions, you're really talking about a small number of very simple geometries. They're just quotients of, I don't know what to say.
Of Minkowski space.
Minkowski space, basically, or
I'm
subsets of Minkowski space.
Okay.
And yet you have this whole complicated formula. Is all that really hidden just in quotients of Minkowski space, or is it just somehow the world's most complicated way of describing it? What I mean?
No, I see what you mean. So keep in mind that most of these quotients are singular quotients. Many of them, for example, are orbifolds. Typically, conical deficits are orbifolds.
But you allowed only one, I think.
Sorry?
I think you allowed only one defect or something, or one.
No, I allow a continuous family of them. because I can.
Oh yes, yeah, but I mean just by counting, there's one. It could have a different size, or it could have a different
Yes,
time
but
translation, which I think you left out because you set spin to 0, if I understood. But
I set spin to 0, but that would affect angular momentum, basically.
Yeah.
That would mean that I can move also in the angular momentum direction. But no, most of all, some of the solutions are, some of the conical deficits are orbifolds of Minkowski space, so they are quotients in this sense. They are singular, but they're still quotients. But some of them are not. Typically, if your identification angle is, now let me not say something silly, if your identification angle is not a multiple of 2 pi by a rational number, it is not a quotient of Minkowski space. At least as far as I know.
Why not? Well, I can see that if you have an excess
Because-
instead of a defect, it's not a quotient of Minkowski space. It's some sort of covering space of
It's
Minkowski space minus a line or something like
yes. I mean, I don't think there is a way. Well, okay, let me put it this way: if you take Minkowski space, so time is coming out of the blackboard, and now this is the spatial plane. This is flatland. And here is some origin that we fix arbitrarily, and then you declare that you're going to cut out this region here. That defines the conical deficit. And you declare that you're going to identify this side with this side. If the angle, say, here is 2 pi times the rational number, the quotient of Minkowski space that consists in identifying this guy with this guy is a manifold, is a Hausdorff manifold for the induced topology given by Minkowski space. But if this angle happens to be 2 pi times an irrational number, what you get is something like quotienting a torus by the equivalence relation that consists in belonging to a circle, which is embedded in an whose angular.
I see. When you say quotient, you mean quotient by a subgroup of the rotation.
Yes.
I just meant quotient in the sense of, okay.
So what I mean is that,
you can still identify
strictly
it.
speaking, this quotient, yes, you can always identify it, but
Just won't be a quotient.
on the side of, I mean, if you look at the topology of the thing, it's, for example, it becomes non-separable as soon as this angle is not 2 pi times the rational number. So I don't know if I would dare calling that a quotient. To me, a quotient is really like I take whatever. I don't know, I take this room, identify this with this, I glue it.
Maybe the word quotient is wrong, but there's nevertheless such a space-time.
Absolutely. No, I fully agree.
And it's a nice, it's not non-Hausdorff, it's not.
Absolutely. I definitely agree. Yes. But what I meant is that when you say quotient, you typically have in mind a certain discrete family of identifications.
Quotient was a bad word.
Can you comment back on this spin 2?
Yes.
Can you?
Oh, sure.
You say that your formula shows that it's spin 2.
I guess the right side, what it is a quotient of, that's what I think I said, is the universal covering space of Minkowski space minus a line. Then your group, you see, then it doesn't have to be the rotation group.
Oh, I see. And then, yeah, because you're removing a line, and then, of course. Indeed, yes, that is true.
Z.
Sure.
Then you can do it.
No, that is true, absolutely. No, of course. So your question was about spin 2.
Yeah.
What is the question precisely?
Right, you say it was spin 2. So
Yes. So, sorry, if we can have the light again. So, if you take this partition function written here, you can actually rewrite it as partition function. I'll write the thing and then I'll explain. I will explain what I want to say. So when I said that you can see that the field has spin 2, I meant that when you compute the partition function, essentially at one loop is just a certain combination of functional determinants. The first functional determinant that you find is the determinant for a field with spin 2. But you also find a ghost functional determinant with spin 1. And this is the sense in which I meant that the field that I'm considering indeed has spin 2. But of course, if you look at the representation theory of the Poincare group in 3 dimensions, indeed, there is no genuine spin 2 massless particle. But that's just a statement that there are no particles, that there are no local degrees of freedom. But in the sense of field theory, this guy still has spin 2. That's what I meant.
Okay. No more questions?
Thank you.